Welcome back to AI CodeCast, where we, break down those daily coding challenges and help you sharpen your skills. Today, we're diving into a problem that really gets you thinking spatially. Count unguarded cells in the grid.
Sounds interesting.
Imagine you have like a building layout, like a grid, right?
Mm-hmm.
With security guards and walls. Now, these guards, they've got like superhuman vision. They can see in all four directions. Until their line of sight's blocked, of course. The challenge. To figure out how many cells in that grid are not under a guard's, watchful eye.
A classic visibility problem with like a real-world twist. I like it.
Exactly. It's a classic computer science problem, but with a fun, kind of real-world spin. We'll tackle it together. We'll start with like a straightforward approach, and then we'll level up, use something a bit more optimized. We'll use depth-first search.
Awesome. Let's do it.
Okay, so let's break down this problem a little more formally. Okay, so picture a grid, like a chessboard, laid out in rows and columns.
Okay, got it.
Now, imagine each cell on this grid is labeled with coordinates, starting from 0. That's what we mean by 0 indexed. So the top left corner of our grid, that's 0, 0. The cell to its right would be 0, 1, and so on.
Okay, makes sense.
Now, the problem gives us two arrays, guards and walls. These arrays, they contain the coordinates of, well, all the guards and walls on our grid. So, for example, if a guard is at, say, row 1, column 2, you'd see 1, 2 in the guards array.
So we're given the locations of all the guards and walls up front.
Exactly. To make this a little more visual, let's jump into example 1. We're given a 4x6 grid. That's 4 rows and 6 columns. Okay, there are 3 guards strategically placed on this grid, and of course a few walls. Now, if we carefully trace each guard's line of sight, right, remembering those walls, we find that 7 cells are left unguarded.
In this example, it's relatively small, right?
Yeah.
But the problem, it mentions the grid could be as large as like 100,000 rows and 100,000 columns. That's huge. And that's where, the efficiency of our approach, it becomes really, really important. A small grid, we can visualize that. We can even solve it manually. But a massive grid, forget about it.
You got it. That's a really great point. And to make things a little more, complex, the problem also says that each guard and wall, they occupy a unique cell, so no overlaps. That does simplify things a little, though.
Yeah, that helps.
So, okay, we have all this information. How do we even start solving this thing? Let's begin with, the most basic approach, the brute force approach.
Okay.
So with brute force, we check the visibility of each cell in the grid one by one.
Systematically.
Yeah, systematically. We could do this by going through each guard and for each guard, checking for any obstructions like walls or other guards in all 4 directions, north, south, east, west.
Makes sense. But I'm already thinking, what are some potential issues developers might bump into when they're, trying to implement this brute force solution, especially with those massive grids we talked about?
That's a fantastic question. One thing that comes to mind is, redundant checks. Imagine you're checking the same cell multiple times, but from the perspective of different guards.
Right.
That's just wasted computation.
Right.
Especially on a large grid. Another pitfall, maybe inefficiently handling those line of sight checks could make your solutions super slow.
Exactly. Those redundant checks can really slow things down, but, there are ways to optimize even a brute force approach. For example, you could use a data structure, a set. It only stores unique values, so it automatically prevent those, those redundant checks, like creating a VIP list of guarded cells, but each cell appears only once.
That's really clever. So even with brute force, there are ways to make it more efficient. But let's step it up a notch. Let's talk about depth-first search, or DFS.
Okay.
Imagine each guard has a flashlight, and they shine that light, in each direction. The light travels in a straight line, right, until it hits a wall, another guard, or the edge of the grid. DFS is like simulating that process, but systematically.
Like exploring a maze. You start at a point, you keep going down one path until you can't anymore, if you hit a dead end. You backtrack, go back to the last intersection, try a different path. That's DFS in a nutshell. It explores one path as deeply as possible before backtracking and trying others. It's super powerful, used everywhere.
That's a great analogy.
Yeah.
Okay, so how do we actually use this DFS to solve our problem here?
Well, we start by representing our grid using a 2D array. Each cell in the array, it's going to hold a value. It'll tell us its state. Unguarded, guarded, guard, or wall.
So we're making like a digital blueprint of our building. Each cell matches a space in the building.
Exactly. And then we, initialize the grid. We place those guards and walls based on the input arrays, the ones we talked about earlier.
Okay, so we set the stage. Where does the actual searching come in?
That's where our DFS function really takes the spotlight. The heart of DFS, it's this recursive function. Let's just call it DFS. This function, it takes the coordinates of the current cell and the direction we're going in as input.
Okay, so this DFS function, it's going to, like, explore each path from where the guard's standing, right?
Yeah.
Marking cells guarded along the way, like that flashlight beam.
Precisely. And within the function, we have rules to, stop the exploration. We call them base cases. The DSS function stops if it hits a wall, another guard, or the edge of the grid.
Those base cases make sense, right? They're the boundaries of our exploration.
Exactly. And here's where the recursion comes in. If the current cell is unguarded, we mark it as guarded because, it's now in the guard's line of sight. And then we call the DFS function again, this time for each adjacent cell in the direction we're exploring. That flashlight beam just extended to the next cell.
So like a chain reaction of those flashlight beams. We're going down each path from the guard, marking cells as guarded until we hit a wall, another guard, or the edge. Got it.
Exactly. When the DSS function, hits one of those base cases, it backtracks, starts exploring in another direction. Keeps doing this until every possible path from the guard's position has been explored.
I see how this systematic exploration is going to, ultimately solve the problem.
It's systematic, which is what makes DFS so efficient. But before we, dive deeper into how it all fits together in our main function, let's take a little break.
And we're back with AI CodeCast. Glad to be continuing this deep dive into the count unguarded cells in the grid problem. Before we pause, we were really getting into, like, the core of how to use depth-first search to solve this thing.
Yeah, that flashlight analogy really helps visualize how the recursion works. Like each guard is, methodically sweeping their flashlight beam across the grid, marking each cell they can see.
Right. Okay, so now let's zoom out a bit. Let's talk about, how we, like, orchestrate this whole process in our main function.
Yeah, we need to tie it all together, right? Like initializing the grid, placing those guards and walls, and then finally calling our DS function. Exactly. So the main function, this is where it all happens. First, we initialize the grid, marking every cell as unguarded. Then we place the guards and walls based on those input coordinates, the ones from the guards and walls arrays we talked about.
Okay, so we have our digital version of the building layout. Guards and walls are in position, and all the other cells are marked as unguarded.
Precisely. Now, for the big finale, we go through each guard on the grid. For each guard, we call our DFS function 4 times, once for each direction, up, down, left, and right.
Like the guards shining their flashlight in every direction, marking cells guarded as they go.
You got it. Once we've done that for every guard, we have a grid where all the guarded cells are, identified.
To get our final answer, we just count the number of cells that are still marked as unguarded.
That's it. It's methodical, and it makes sure we check every cell's visibility.
This breakdown makes it really clear how DFS tackles the problem. It's systematic, it's efficient, and we're not going to miss any unguarded cells.
Now, while we're talking about efficiency, let's talk about the time and space complexity of this DFS approach. Whenever we're, dealing with algorithms, it's really important to think about how much time and memory they're using, especially when those grid sizes get massive, like the problem mentioned.
Right, we don't want our solution to take forever or use up all of our computer's memory.
Exactly. So for time complexity, DFS has a complexity of OMN, where M is the number of rows in our grid and N is the number of columns.
So the time it takes to run the algorithm increases linearly with the size of the grid. That makes sense. Because in the worst case scenario, we might end up visiting each cell in the grid, at most once during those DFS explorations.
Exactly. Now let's think about space complexity. The space complexity is also OMN.
That's mostly because of the grid itself, right?
Yeah.
Which takes up MN space to store all those cell values, unguarded, guarded, guard, and wall.
Right. We also have to consider this space used by the recursive call stack, but that's usually less significant compared to the space used by the grid.
So overall, DFS is a pretty efficient solution, both in terms of time and space.
Definitely. It's a good balance between, performance and how relatively simple it is to implement.
Now, before we wrap up this DFS talk, I want to touch on, its relevance in general. I mean, it's not just for counting unguarded cells, right?
You're right. DFS is like a core algorithm. It's used for traversing graphs, and it's got applications all over the place.
I was thinking that. It's like we're adding a really powerful tool to our coding toolbox, something we can use to solve tons of problems, not just this one.
Exactly. One classic use of DFS is maze solving. Our grid problem, if you think about it, it's kind of like a maze where the guards are, trying to find all the paths they can reach.
And the walls are like obstacles in the maze, blocking the way.
Precisely. DFS is also used a lot in pathfinding algorithms. Those are used to find, like, the shortest or fastest route between 2 points.
Like those navigation apps, the ones we use all the time to find the quickest route.
Yeah. They're probably using some variation of DFS or other graph traversal algorithms in the background.
It's cool to see how these seemingly abstract algorithms are used for such practical things.
Totally agree. And even in game development, DFS is super important there. Imagine you're making a game with, like, these complex levels, and you need to figure out which areas the player can actually reach.
You could use DFS to like map the whole level and figure out which parts are accessible.
Exactly.
So knowing DFS opens up a ton of the possibilities in computer science and, even beyond that.
And that's what we're all about here at AI CodeCast, taking on these daily challenges, and learning those core computer science concepts that we can apply in so many different areas.
This has been super insightful. We went from counting unguarded cells to, really understanding the power of depth-first search. Now, before we move on to our final thoughts, I'm curious. We've been assuming our guards have perfect vision, unlimited range. What if we, made things a little more realistic? Like, what if we gave the guards limited vision ranges?
That's a good point. Adding limited vision would definitely make the problem more challenging.
Right. Our DFS approach would have to be tweaked a bit to handle those limited ranges. Instead of exploring a path until we run into a wall or another guard, we'd have to stop when we reach the guard's maximum vision distance.
Exactly. Basically, we'd need to add a distance parameter to our DSS function, to keep track of how far we've gone from where the guard's standing.
And that would stop us from marking cells as guarded that are, too far away for the guard to see.
Right. It just goes to show that even a small change to the problem can make things a lot more interesting and force us to, adapt our algorithms.
That's what keeps things fun, right? Always pushing ourselves to think outside the box and come up with new solutions.
Absolutely. And that's the perfect lead-in to our final part. We'll wrap up by, revisiting the key takeaways from our deep dive into this problem, and then leave you with some final thoughts to think about.
Sounds good. We'll be right back after a quick message to dig into those final thoughts and wrap up our exploration of this really cool challenge. And we're back, AI CodeCast. We've been exploring this count unguarded cells in the grid problem. It's been, quite a journey.
Definitely a lot to unpack.
We covered so much. Understanding the problem, trying out brute force, then, diving into depth-first search.
Yeah, a lot of ground covered.
So let's recap the key takeaways before we wrap up.
Sounds good.
First, it's so important to really understand the problem.
Absolutely.
We broke down the problem statement, clarified those important terms like zero indexed. We visualized that grid with the guards and walls.
Yeah, like laying the groundwork. Before you build a house, got to understand the blueprint, right?
Exactly. Then we explored that brute force approach.
The classic.
Maybe not the most efficient, but a great starting point. It helped us see the logic behind the problem.
It's a good foundation.
And we even talked about ways to, optimize that brute force approach.
Yeah, like using a set to avoid those redundant checks that can make your code super slow.
Right, those optimizations. They're helpful, even when we move on to more advanced algorithms.
For sure.
Then we got to depth-first search, DFS.
The real star of the show.
It's way more efficient for systematically exploring that grid and finding those unguarded cells.
Definitely. And we went through the step-by-step process of the DFS function, really getting into the details.
That flashlight analogy. Super helpful for visualizing how the recursion actually works.
It really paints a picture, each guard scanning with their flashlight, marking every cell they see.
Right. And we talked about the time and space complexity of DFS.
Yeah, both O, M, N, where M is the number of rows and N is the number of columns.
So the time and space our algorithm needs grow directly with the size of the grid.
Makes sense. Worst case, we might have to check every single cell.
But the cool thing about DFS is that it's so systematic and efficient.
It's a lifesaver for these kinds of problems.
And then we realized DFS isn't just for this one problem.
Oh, not at all.
It's used for all sorts of things. Maze solving, path finding, even game development.
Like having a multi-tool, a Swiss Army knife for your code.
Love that. Okay, before we say goodbye, let's leave our listeners with something to think about.
Always got to have that final thought, right?
We've talked about guards and walls that don't move. But what if we added moving targets? Like people walking around.
Oh, things just got interesting.
Our goal would be to track how many people are in a guard's line of sight at any time.
That's a whole new level of complexity. We'd need to figure out how to show those moving targets in our grid. Maybe update their positions like every second.
Right. And our algorithms would need to adapt to that, constantly recalculating the guarded and unguarded cells as those targets move.
A real challenge, but it builds on what we've learned.
So listeners, if you're feeling adventurous, give it a shot.
See if you can adapt the brute force or DFS methods to handle this new challenge.
And if you come up with something awesome, share it with us.
Yeah. We love seeing the creativity of the AI CodeCast community.
That wraps up another episode. Thanks for joining us on this deep dive into algorithms and problem solving.
Keep coding, keep challenging yourselves, and we'll see you next time for more exciting adventures here at AI CodeCast.